All right, so we have, let's see, I still haven't looked at the syllabus. Is CYK is due this week, right?
Yeah, I think so. This Friday.
Sounds right to me.
Yeah, I try to always have things due on Wednesdays, but I figured that since this was the week where there wasn't going to be an assignment due, it made sense to make CYK due here. And that way you're not overloaded with CYK and an assignment at the same time. So I think it makes sense. I will have office hours an hour after this class ends. For those of you who are working on that, would like some assistance getting started, some assistance getting through some of the more complicated sections, determining the data structures that are embedded within it, how to parse the file. I have very intuitive ways of describing all of that. So that's something that's where you are. I'd be happy to talk to you about it. Last time we were talking about this concept of the universal language, which was the language of all machine string pairs, where the machine is a Turing machine, the string is a string accepted by that Turing machine, and we wanted a Turing machine to be able to recognize that language, that takes as input a machine string pair and determines, does this machine accept this string or not? So that way we would be able to output every possible machine string pair and just have a way to produce whatever it is, all such programs that could be made in a higher level language or with a Turing machine. We would have an enumeration procedure for that, which is really strange to think about. There is an enumeration procedure out there that generates new program forever. And you could not give me a program that enumeration procedure would not generate. So that is the result of saying that the universal language is recursively enumerable. There will be some machine string pairs where that machine goes into an infinite loop on that input, but because we can diagonalize, as we described with recursively enumerable languages, then it's not actually a problem. We will accept all such strings that can be accepted, all such machine string pairs strings that can be accepted. And that is a really cool theoretical result. So we started this process. We want to show that it's recursively enumerable, so we construct a Turing machine called the universal Turing machine to recognize it. We said it's a multi-tape Turing machine. First tape was the encodings of M and W. So all such MW pairs are just infinitely on that tape. You can imagine that there is some extra process writing to this tape while this is going on, so that there's not an infinite amount of material that's already pre-constructed on this tape. We would have some kind of generation procedure that continues to add to this tape as we go. Second tape is simulating M's input tape. So we are reading from the definition of M, which is again is embedded in tape 1, the definition of M. We can, using that information, be able to simulate the input tape left and right, possibly state. Third tape keeps track of M state, and again we get to see what states it contains and the associated transitions on the first tape, because that's where M is, the definition of M is stored. And finally, we have a scratch tape. So we can keep track of the simulation of M on W with this universal Turing machine. And it's reprogrammable in that as soon as we read a new M, we can change tapes 2 and 3 to represent the new Turing machine's states and transitions. So yeah, search tape 1 for a transition of the current state of M, which we store on tape 3, and the current tape symbol of M stored on tape 2. Then we change the contents of tape 3 because we transitioned to a new state, so we change tape 3 to be that new state. We change the tape symbol on tape 2, moving past the associated symbol in W. Then we move the tape head left to right on tape 2 as well, as specified by the associated transition. So we have a full ability to emulate this process. And note that since it's recursively enumerable, this process may go into an infinite loop, but if we only simulate one move at a time, we will initiate all 4 of these tapes, make a single move on it, store that result, wipe it clean, load the next one. So we would be going back and forth between the M's and W's on the first tape as we diagonalize and finish or don't finish that. But it's a process that would continue to work and continue to look at new strings, even if one goes into an infinite loop on a particular machine. So the language of the universal Turing machine is the universal language. And what's amazing about this is it's all the elements of a modern stored program digital computer.
I was about to say, it kind of sounds like an operating system time slicing
Yeah.
between running programs.
Yeah, it is the simplest way to do something like that with the least complexity. Obviously, modern operating systems do not do this. It's way too suboptimal. It is horribly inefficient. But what it does is it proves that this is possible theoretically with some machine. And if we can utilize modern computation power to turn this problem into an easier problem with respect to time, then what we have is the ability to show the limits of algorithmic computation, which is actually the focus of the next slide deck that we're going to go into. So show that it is recursively enumerable. The next thing to show is that it is not recursive. Because if it were recursive, then we'd be able to answer yes or no in a finite amount of time. But if it do, again, as usual, we proceed with a proof by contradiction. We suppose that the universal language were recursive, then there's a Turing machine that accepts the complement of it. We learned earlier that the complement of a recursive language is recursive. Whereas the complement of a recursively enumerable language, we can't state anything about. But we will now accept the complement of the universal language. So we transform the machine into a new machine that accepts what we're going to describe on the next slide, the diagonalization language. So we'll transform the input string into duplicating it. So we have a duplicated input pair, WW. We will simulate M on WW, assuming that the first W is an encoding of some machine, M sub I. The second W is an encoding of some binary string. Since M accepts the now complement of the universal language, as we stated at the very beginning via our assumption, then M will accept WW if and only if M sub I does not accept W sub I, which is a prediction. So we do this with an instantiation of a language that we know to be recursively enumerable. We prove the diagonalization language, as we're about to do, is recursively enumerable. Then we have M prime accepting W if and only if W is in the diagonalization language. And if there is no Turing machine that recognizes the diagonalization language, then there is no Turing machine that can recognize the complement of the universal language, which would prove that it's not recursive. That's kind of a mouthful. So this is the outline of the proof. But let's actually go dive into this one section that is the diagonalization language and try to understand what that is and why that is not recursively enumerable. All right, diagonalization language says, let this infinite sequence of strings, W1 on forever, is an enumeration of every single binary string. Already an infinite number of them, since they can go on forever, but we have some enumeration of all binary strings. We will say, let M sub 1, M sub 2, etc. on forever be an enumeration of every possible Turing machine. Then we will say the diagonalization language is all strings such that that string is not in the language of that machine. So we're looking at string 1, machine 1, string 2, machine 2, string 3, machine 3, and we don't care about anything else. It's just diagonalizing the enumeration of all binary strings and the enumeration of all Turing machines via some enumeration procedure for each. How do we say that the diagonalization language is not recursively enumerable? It ends up being exactly the same Cantor's diagonalization proof. We say, suppose that it does. Suppose the diagonalization language is in the language of the machine for some machine with that same subscript. What does that machine do on W sub I? If that machine accepts that string, then by definition, it can't be in the diagonalization language. But if the machine does not accept the string, then by definition, the string is in the diagonalization language. So, since that string can neither be in the diagonalization language nor not in the diagonalization language, you have to conclude that there is no machine that can define the diagonalization language. How are we doing with this? Does that make sense?
I think. Almost, almost there, yeah.
So an enumeration of every machine, an enumeration of every string. So the diagonalization language says that by definition, it is all strings such that that string is not in the language of that machine. So we zone in on one of them, like machine 5, string 5. We now say, does machine 5 accept string 5? If it does accept it, then it can't be in the diagonalization language. If it does not accept it, then it is in the diagonalization language. The diagonalization language is all languages of machines for some Turing machine I. And it ends up kind of neither being in the diagonalization language or not being in the diagonalization language. So the conclusion is that such a machine that recognizes the diagonalization language can't exist. So we go back to the last slide and we plug that in and use that to conclude that the complement of a recursive language, that is the universal language, can't also be recursive. That is the general proof form. Do we see the contradiction?
I think so, right? Because so. When we say diagonalization language.
It's all strings such that that string is not in that machine. But if M accepts W, then by definition, it can't be in the diagonalization language. But the diagonalization language, if it doesn't accept by definition, it is in the diagonalization language. And by definition here, that string is neither in the diagonalization language nor not in the diagonalization language.
You were to like map one machine to like many strings, right? Every string it doesn't accept, and then the strings would also map to every string
Yeah.
that, or every Turing machine that doesn't accept it.
Yeah, it kind of creates an, if it doesn't, then it does. If it does, then it doesn't. So we conclude kind of a both. It's a both slash neither, neither of which is logically possible.
There's a lot of knots in the string, and it doesn't make it easier for us.
Yeah. Understanding this is not vital to the class itself. I just wanted to throw a couple of the how we go do this on the slides so that we could talk about them. I'm not going to query your understanding of this at a reasonable level on an assignment or on an exam, mostly just to show how it works. The important takeaways are that the universal language, the universal Turing machine and the universal language are recursively enumerable, but not recursive. That is the important takeaway. the conclusion of this work. Questions before we move on to a really weird concept? We have we're just in the part of the class that is weird concept after
Yeah.
weird concept, and it's great.
I was about to say, unlike the concept we were just talking
Yeah,
about.
right. So we know that there are grammar types that are equivalent to regular languages. We had regular grammar that mapped to regular languages. We had context-free grammars that mapped to non-deterministic pushdown automata. So I'm going to introduce a new grammar type, and the question that I will have for everyone is, what language class that we have talked about does this grammar class map onto? So I think I stated before that context-free grammars have no restrictions on their productions. That was not actually true. There is a restriction on context-free grammar productions.
You can only go from left to right. Is that it?
Kind of. There is a restriction. It's just not a restriction that most people grasp on the first hand, which is the left-hand side was restricted to be a single symbol, a single non-terminal. So to move to an unrestricted grammar, we are going to allow for multiple symbols, terminals or non-terminals, on the left-hand side. So we have the full ability to replace any terminal, non-terminal sequence with another terminal, non-terminal sequence. There is one restriction to this, though. So we're relaxing even these constraints. Any number of terminals or non-terminals on the left-hand side or right-hand side of a production, we need at least one terminal or non-terminal on the left-hand side. You can't have something like lambda goes to. That makes no sense. So lambda not allowed on the left-hand side of a production. We'll start with the easy question. More, same, or less powerful than context-free grammars?
I'm gonna go with more.
You would be right. There are languages that we can represent with an unrestricted grammar that we cannot represent with a context-free grammar. Now the question I have for you is, more, same, or less powerful than recursive languages?
Same or more.
That's probably a good gander. I like identifying it's not less powerful than recursive is good, and you would be right.
I'd be tempted to say same, because I feel like a language is somehow just more general than a grammar, right? Because like a grammar is kind of like a machine in that it's kind of a dense definition, but a language is just so broad, it's just a very simple, like.
The intuitive way that I think about this is there a way to generate a larger and larger and larger and larger and larger string sequence where you can't prove that this grammar will ever produce a string or not a string? Will it be able to loop forever and not ever end up in a string? Or is there a way for it to terminate and represent a string after 10,000 iterations, 10 million iterations? That would be what maps it onto recursively enumerable versus recursive. Recursive, we can always answer yes or no in a finite amount of time. Given that this grammar has been applying production after production after production after production, is there a way to guarantee termination? A way for us to know whether this will terminate?
Wouldn't that depend on the grammar itself? Like,
Right, but could you produce a grammar of that type with these rules? With a context-free grammar, we have the ability with a parse tree to determine whether it will finish or not. Is there a way to do that with this? It had to do with the fact that we were always expanding non-terminals, but as soon as we allow for terminals or non-terminals on the left-hand side, we will lose that guarantee.
yeah, what if there's just like two transitions that like loop on each other and it never stops?
Yeah.
Can't say that it ever does.
Yeah, I think an unrestricted grammar could potentially be like impossible to predict that it's going to.
So, in fact, it is more powerful than recursive languages. Now the question is it more powerful than recursively enumerable languages?
Oh, I think I got those mixed up. So is recursive more powerful than recursively enumerable?
No, it is less powerful. Recursively enumerable is more powerful.
Okay, recursively enumerable. I want to say it's the most powerful.
Yes, the most is powerful that we can that we can recognize. I like it.
I'm gonna say less. I think it's less powerful than a recursively enumerable language. That's fine.
We have one vote for same, one vote for less.
2%.
2 for same. The sames have it. It is actually perfectly mapped onto recursively enumerable languages. Turns out that Turing machines and unrestricted grammars have exactly the same power, the ability to recognize recursively enumerable languages. Which is pretty wild to think about, that there is some transformation out there that converts an unrestricted grammar into a Turing machine program, or a Turing machine program into an unrestricted grammar. That said, it's incredibly challenging and not remotely efficient. So how do we do this with an unrestricted grammar? Start with the start non-terminal. Then we're going to find all strings that can be derived from the start state within a single step. So we say, starts with the start non-terminal. Every grammar has to do that. S arrow something. And then from there, there can be anything on the left-hand sides from there. But we look at one step, applying S arrow, what strings can we produce within that one step? Then that becomes the internal nodes of that tree. And for every one of those one steps that we can get away, we look 2 steps.
Iterative deepening.
It is very much like iterative deepening. So we continue this process for all possible number of steps. This process does not terminate. All such strings that can be produced within 3 steps, within 4 steps, within 5 steps, but it is an enumeration procedure for all strings that can be represented by this grammar. You cannot give me a string that can't be derived within some finite number of steps. So this iterative deepening procedure will eventually reach the point where it can generate that string. Because the string has to be finite length. And we will generate that within some finite number of steps if the grammar can produce it. Of course, if the grammar can't produce it, will this process ever terminate and say no? No. So it kind of spins forever in that sense, which is another way to latch yourself onto why this is recursively enumerable. We can't really answer no, a string is not in this language, because it may be that there's just a really convoluted path to generate it that involves more steps than you've looked at so far. Since there's no restriction whatsoever, it could be that we blow up a string to size 10 billion before it shortens back down to this 4-character string. There's nothing that says that that's not what happens. So process doesn't terminate, it continues to produce new strings, but it is an enumeration procedure and can be mapped to a Turing machine. On the other hand, converting from a Turing machine to an unrestricted grammar is not that easy. You remember what a converse is?
It's Q plus Q, Q plus P.
Yeah. Inverse is not P implies not Q, converse is Q implies P, contrapositive is not Q implies not P.
Forgot those after the exam. This was
Well, here I thought it was a brand of shoe.
I should launch a brand called Contrapositive.
That'll be extra wide Converse.
So given a Turing machine, derive an unrestricted grammar accepting the same language. There's a really long proof in the book. It's kind of gross. I don't want to go through it. You probably don't want me to go through it. Check it out if you're interested. But unrestricted grammars are a cool class of grammar that really show, again, the limits of algorithmic computation. There's another grammar type we might care about called a context-sensitive grammar. There are quite a few of these classes of grammars between context-free grammars and unrestricted grammars, but it turns out that Most of them don't tell us anything new or interesting. But there is this one class, context sensitive, that is worth mentioning in some capacity. It produces the same class of languages that linear bounded automata do, which, if you recall, was if we allow for a linear portion of the tape, and we only allow for computation over the amount of tape that you have. So you don't allow for computation outside of, you start with a strings representation, you don't get more memory than the string can take up. If the string is long, you get a bit more memory. If the string is short, you get less memory, but you never get more than the string had in the first place. So, rules for context-sensitive grammars. It starts exactly the same as unrestricted grammars, but then we place some restrictions on this. So one or more terminals or non-terminals allowed on both the left and right-hand side of any production. But we need the following condition to be met. The number of terminals and non-terminals on the left-hand side of every production must be less than or equal to the number of terminals and non-terminals on the right-hand side. So we can't go from more to less. We can only go from less to more. That seems counterintuitive at first. Why is that a restriction that is meaningful? And it turns out that now we can start to answer no once we have enumerated some number of processes. Once we've seen and gone through some number of steps of this. If we're trying to derive a string of length 4, at some point we can say this grammar can no longer produce a string of length 4. It has to produce something longer than that, which allows us to reject. So length of successive string forms only increases. And this means, since we can't go from non-terminals, like eventually those non-terminals have to turn into terminals in some way, shape, or form. Because you can't go from 5 characters to 3 characters. You can only ever go from 5 characters to 5 or more characters. So by the time you derive a string that is longer in terminals and non-terminals than your query string, you can reject. Because you can't possibly create that anymore. So context-sensitive grammars can be written into a particular normal form. X capital A Y, arrow X B Y. So the form capital A to V can only occur when A appears in the context between strings X and Y. So that's why we call it context sensitive. The non-terminal for that has the associated context of being in between a terminal that appears before it and a terminal that appears after it. Questions on any of this so far? Yeah.
How would you handle left linear, right linear in this context? Because you could have a substring that doesn't map to a production yet, and then down the line, maybe I do one on this side, and then now this is in the proper context. Is it like after I've done that, okay, now my most left?
Yeah, so yeah, linear has to be read from left to right or right to left. This can, of course, recurse in the middle of something. So if you were referring to something like that, then either your X or your Y would be the beginning or the end of a string. You can't use lambda as a reasonable terminal. So the context for that would be it's at the beginning or end of the string. Let's give you an example of this, because I feel like this is good enough to warrant an example. So we can't generate the empty string at all because of that rule. There must be at least one symbol on the left-hand side to start the start non-terminal, and you can't produce less than that. So they can't derive the empty string. Let's show that A to the n, B to the n, C to the n is context sensitive. So remember that this was a language that was not context free. We showed that with the context free pumping lemma, but then we wrote a Turing machine for it. So context sensitive sits in between these classes. Since Turing machines represent recursively enumerable languages, or can represent those, and context free, we showed this was not, so it's somewhere in between. It turns out that it is context sensitive. But it turns out that this is really difficult. Even as such, but let's spend a little bit of time and see if we can figure this out. So remember that you can have any number of symbols on the left-hand side or right-hand side, as long as it's one or more. But you can also have terminals paired with non-terminals. I'll be curious if anyone thinks it can come up with an answer to this. It is not easy. I'll lead with that. This is not an easy construction. What are people doing? This looks like, it looks like people are either stuck deep in thought. What was it like to get started with this? Let's at least check in with you about how this is going. Where are you hitting a wall if you're hitting a wall?
Well, I feel like we're trying to expand. It's the problem of like synchronizing the expansions of
Yeah,
right. So, like you basically pick like, is it between A and B or B and C? Then I'm going to try to like synchronize this, and then trying to figure out maybe you can take advantage of the fact you can recognize non-terminals on the left-hand side to do something with that. Maybe you have to also rewrite a non-terminal back to a terminal somehow. I'm still
yeah,
trying to figure out how to phrase it.
smart.
A similar issue, but I think like where I'm gonna expand is always challenging to determine. What I've started doing is if I want to expand A's, it's only gonna happen where the A and B's meet.
Yep, smart. Very smart. Yeah, there are two important locations in this string A to the N, B to the N, C to the N. It's where the A's meet the B's and where the B's meet the C's. And you need some way to alternate back and forth between those two locations. And then you need to do something at each of those two locations, allowing yourself only to terminate the grammar when you're at wherever it is that you started. So you start kind of with an ABC. The goal is to produce AABBCC from that. So you're going to insert something, move, insert two things. Move back, insert one thing, move back, insert two things. Move back, insert one thing, move back, insert two things. The question is, how do you move back and forth? And the answer is, let's just go over the answer, because I think this is a really fun exercise, but I also don't really expect that people can construct this without more time and effort, but let's at least go through an example of this. So if we start with S going to, oh, that's interesting. I picked up this orange pen that someone left in here, but they put red ink in it, so that's fun. I'm actually colorblind today, and it's a very interesting orange. So if we're producing ABC, then we can immediately terminate and produce that ABC. If not, we're going to go through a loop that allows us to produce an additional A and B and C in the appropriate places. So that gives us A, B, C. From here, we recognize this AB as that AB. So we can make the associated substitution, and this is how we're going to move this A non-terminal to between the A's and B's to between the B's and C's. So this just shifts where that A is. So this becomes A, B, A, C. So now the A is between the B's and C's. When we see AC here, we can replace that AC with the associated new non-terminal and making the second set of C's as well. So this becomes AB, but now I've replaced the AC with B, adding a second B, and CC, adding a second C. So now we have the ABBCC, and now we need to go back and add the last A. So we are going to recognize that BB is right there, so we can swap them back to start shifting this back toward between the A's and the B's. So we will do that. A capital B, 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 C, C. And then this AB can either become AA and terminate, making AA, B, B, C, C and being done, or AA capital A, which says now we're going to go through this process again and make another A and B and C. So let's do it one more time just to show this could become AA, B, B, C, C. But if we don't, then we have AA, capital A, replacing that AB, B, B, C, C, and we see how now this is very similar to this capital A between A, B, C, between the A's and B's. It's exactly the same here, the capital A is between the A's and the B's. So we go through that, we see the AB, that becomes a BA. Move it, expand it, move it back, produce it. I think that's probably good enough for you to see that this is in fact the same as that. And we will just continue through that process to produce an extra A and B and C.
So like the one non-terminal is almost like the head of the Turing machine going through the
Yeah.
like certain characters.
Yep. But it's context sensitive in that this always has to go to something that is more than or the same number of characters. So it turns out that we don't need more space on a Turing machine than just the input to be able to do that, which is kind of cool. But it is kind of similar to how a Turing machine works as well. We'll find that this is true in a lot of context-sensitive grammars, that there is a lot of replacing of a couple characters with a couple of characters in order to shift our variables around. So that is a common technique that is used in this type of grammar. I will not have you doing many context sensitive grammar. I won't have you doing any of this on exams. There might be a homework question or two asking you to come up with a context sensitive grammar, but. Yeah, this is not the most important topic. I just find that it's fun to look at all the different language classes and their associated forms and how that changes, so you get a sense of what you can do to a grammar to produce different language classes, what you can do to an automaton to produce different language classes and how they map together. Any questions on that? I shouldn't have erased it before asking that, but any questions on that? Here's an example of the actual writing out of AAA, BBB, CCC. So yes, derivation of that. We know that context-sensitive languages are more complex than context-free languages, but we can show that it's a subset of recursive languages as well, but they are not the same. We could show that recursive languages are not necessarily context-sensitive. And we already showed that with the fact that linear bounded automata are less powerful than a simple Turing machine. So we actually don't have to go into it, since we can map them to those associated languages. And that gives us what I've already shown in this class. This is where this finally shows up, the Chomsky hierarchy. So now that we've actually looked at this and fully explored all of these language classes, it makes a little bit of sense to show you visually that we have regular languages. All regular languages are deterministic context-free. All deterministic context-free languages are context-free. All context-free languages are context-sensitive. All context-sensitive languages are recursive. All recursive languages are recursively enumerable. So that's the subset way of looking at these classes of languages that are all inside of each other. But then we also studied a couple more that were inside of context-free, which was the deterministic context-free and linear. They're all regular, sorry, they're all context-free. Regular is each of those, linear and deterministic context-free, but there are some linear languages that aren't deterministic context-free and some deterministic context-free languages that aren't linear. And linear is different from context-sensitive. So we've covered a lot. We've talked about a lot of different language classes in this class, which is pretty impressive that we've done all that in the short amount of time that we have. Right? Right? We've been on a breakneck pace in here. We've done a lot. But where this is all headed is a real discussion on the true limits of algorithmic computation. So what is that boundary between languages that are recursively enumerable and not recursively enumerable? And what kinds of problems are in this language class of not recursively enumerable? What kinds of questions could we not answer if we had an infinitely powerful computer? There's no time constraint. Any amount of time will pass instantly. What could we still not answer? So we've discussed at length what Turing machines can do, but what about what they cannot do? Any thoughts on this? Any guesses? So we've talked about some silly things like real numbers. We talked about some things like the power set of an infinitely countable set, infinite and countable set. One person mentioned this earlier this quarter, but there is a very important problem in computer science that is studied because we can't solve it.
P equals an P.
That is potentially one of them. We actually have no proof one way or the other about whether that is true or false. Guesses are that it is false, and we just can't prove it. So that is a very good one to latch on to.
How to center
But there is one we have proven.
Center it.
There's a problem that we have proven.
Okay.
And the fact that we are this close to this means that tomorrow is going to be movie day. There's one day in here that we get to actually watch the video, and it's a very informative Veritasium video on this exact problem and more of it. But it is the halting problem. So
Oh, yeah, yeah.
for those of you who have heard of the halting problem, it is the problem of whether we can determine algorithmically whether a Turing machine will halt on a particular input. And this is another one of the harder problems to understand in computer science. It took me a very long time to come to an intuitive understanding of this problem because it was not taught to me intuitively. I remember back to my first, second class that dealt with automata theory in grad school. And I had a professor who would explain things like how automata worked, and he would have no context for this. He would just start class with this: apple automata, banana automata, apple and banana automata. See? And the entire class would just kind of blink a few times. Don't know what you had before class, but we want some. And yeah, it was kind of the same way that the halting problem was explained. It took a while to try to understand that, but we will come back to this tomorrow, talk about these concepts of computability and decidability, talk about the halting problem, and then dive into an understanding of how the halting problem came to be asked. And a lot of the kinds of questions that the limits of algorithmic computation talk about, because the limits of algorithmic computation turn out to also be the limits of mathematical computation as well. So using our system of math, what are the flaws in our system of math? What can math never answer for us? Which is interesting. This was a huge debate for hundreds of years, and we'll watch a video about exactly what that debate was and the results of that debate and how that informs computer science and computability in computer science. So I will see you tomorrow for that.
Would that be like trying to predict infinity or something?
Well, we have a very solid understanding of infinity. There are just some problems that we can never solve. One of them is the halting problem. I give you basically, I would ask you, can you write a program for me that takes as input another program and tells me, and an input to that program, telling me whether that program will halt on that input? You can analyze a particular program and figure that out, and you can write a program to do that for a particular program, but in general, can you write a general program that takes a program as input, and input to that program as input, and tells me whether or not that program terminates on that input? And the answer is no.
Do you use symbolic execution?
You could not.
No.
There is no way to do it.
I don't know, I mean, I feel like it's a pretty broad term, but